Hello everyone, welcome to topic 9.2, absolute entropy and entropy change. By the end of this, you should be able to calculate the entropy change, or delta S, so change in entropy, for a chemical or a physical process based on the absolute entropies of the species involved in that process. So there is an equation, and we will discuss that and then practice with it in these notes. So entropy, delta S, can be described both qualitatively and quantitatively. In definition, entropy is the measure of disorder in a system. In 9.1, entropy was described qualitatively. We were able to determine if the process showed an increase or decrease in entropy. Entropy can also be calculated quantitatively. The second law of thermodynamics states that the entropy of the universe increases for spontaneous processes and remains unchanged when a system is at equilibrium. So we have our spontaneous process expression here, and the one proving that it is at equilibrium below. Entropy, let's focus on the entropy of a system reaction that we are studying. We can calculate the entropy change, or standard entropy changed, of a system, which is the same as delta S reaction, by adding the standard entropies for the products multiplied by their coefficients and then repeating that for the reactants. You then subtract the products from and the reactants as given in this equation. So there is a link that you can access, but I also want to point out that a while back, R-E-M-E-M, oops, if I could spell, we talked about enthalpy, right? And that enthalpy was also a state function, delta H, and that the delta H of the reaction could also be calculated by, if I could write it, the sum of, and there should, I like to write the N in there where it's the coefficient of the change in entropy for products, and then subtract the reactants from that. Okay. And so they are still, I put delta S and not delta H. So that should be delta H. So here we go. Let's fix it. Maybe. There we go. Okay. Well, that was silly. So we can use a similar process because it's a state function. It doesn't matter where you start or where it doesn't matter how you get there. It only matters where you start and where you end. So your reactants and your products. So if we have a reaction like this one as follows, we can use this sample equation to calculate it. So let's apply this equation to a real chemical reaction. Use thermodynamic data to calculate the delta S for the following reaction. So they were kind enough to give us that data. So we are going to do the delta S of the reaction is equal to 4 times, and then, well, it's coefficient times the compound, so I'm going to come over here to NO2, so 240.1 plus, and then I'm going to do water, so 6 times water, which is 188.8. And then I'm going to subtract the reactants, so 4 times ammonia, and then 7 times oxygen. Okay, so now we'll use a calculator because we're smart like that and determine that delta S of the reaction is equal to negative 114.4, and our units are up here, so joules per mole Kelvin. And remember that delta S, unlike delta H, has Kelvin in there as well. Okay, so let's practice another one. So I want you to pause the video, and using the same process as I do, I want you to calculate the delta S of this reaction. Please pause the video now. Okay, so you should have gotten a positive 603.7 joules per mole Kelvin for this enthalpy of reaction. Okay, you do not have to write the positive sign here. I like to write the signs though in for my state functions because it communicates that it is indeed positive versus negative and helps me to see, is this a spontaneous process in this case, like, or not spontaneous. No, it is spontaneous, right? So like enthalpy and entropy is increasing in this one. It's positive, so this is a spontaneous process, unlike the other one. So by highlighting that, like not highlighting actually, but like including the positive sign, it makes me understand or remember that this is a spontaneous process. So this concludes our notes. Complete the you do, and thank you for tuning in.